Today, I'll be presenting about CI and CD using GitHub Actions and Kubernetes. And just quickly before we start, just want to emphasize that these are my own opinions and experiences. I'm not speaking on behalf of my employer in any official capacity. So to set some context for this talk, I just want to quickly highlight some of the things our team is building. We focus primarily on building a lot of the cloud software and infrastructure behind all of Tesla's energy products. So I've included some posts here highlighting a few of the recent projects where we played a role. We've worked a lot on virtual power plants, adding non-Tesla vehicles to the supercharging network, and residential features like Stormwatch. And we've also worked on a ton of other apps. Unfortunately, there's not enough space for me to even include most of them. But if you're interested in learning more, you can check out the links on this slide, and I'll also include them at the end as well. And if you're interested in learning more about the technical details of the software that we're building, I also won't be talking a lot about that today. I'll be focusing on CI and CD, but I would highly recommend checking out a couple of excellent talks from my colleagues, Natalie and Hector on the left, and Percy and Colin on the right. And I'll also include these links at the end. So let's start with some quick definitions to make sure that we're all on the same page here. So first, what is continuous integration, or CI? So to me, CI is simply the process of automatically validating the changes to your software before merging them and especially before releasing them. So typically this amounts to running some sort of a build pipeline with compilation, linting, and testing steps on every pull request, for example. And then continuous delivery, or CD, is the process of releasing automatically, or if not automatically, then very easily, releasing frequently and ideally in small, low-risk increments. And continuous integration and continuous delivery get grouped together often because they rely on a lot of the same underlying tools. One of those tools is GitHub Actions. GitHub Actions is GitHub's platform for CI, CD, and just general programmatic automation. So I'd like to cover some details on our engineering workflow, as that influences a lot of our choices in CI and CD. So as I said before, we're primarily focused on building cloud software. We work in a few different languages. I happen to work mostly in Scala, but there's also a good amount of Python, TypeScript, Golang, and some others. We deploy our applications primarily into Kubernetes, and we use Helm charts to bundle up all the YAMLs and do some templating. And we use a tool called ArgoCD to handle diffing and synchronizing these resources into the Kubernetes clusters. We have a handful of library repositories, and then we have many more application-specific repos which depend on the artifacts published from those library repositories. As engineers, we write and maintain all of our own tests, and we operate all of the software, including on-call rotations, to make sure that it's running 24/7. All of our changes go through code review and automated testing before we merge. And we make many releases to production every day. We have no fixed release schedule. So given all of that, why does good CI and CD matter to us? So we found that it enables us to have fast and understandable iteration on our software. That lets us make frequent, low-risk releases, which lets us build reliable and robust systems, and that ultimately leads to an excellent customer experience. So another way to say this is that it lets us as engineers stay focused on building the product and allows us to keep moving quickly. So let's jump into GitHub Actions, starting with the primitives. So a trigger in GitHub Actions is an event that happens in GitHub that starts a workflow. So I think there are about 30 of these triggers at this point, but the most common ones that we use are when someone opens a pull request, when a pull request is merged, on a cron schedule, or just running manually. A workflow is the outermost runnable unit that gets triggered by a trigger or an event in GitHub. So we might have one workflow for CI and another one for CD, and they would typically have different triggers. All the workflows are specified as YAML files, and they live in the repository. And there's very little point-and-click configuration involved here, which is nice. A job is the runnable unit within a workflow. So each workflow has one or more jobs, and you typically split a workflow into jobs just to divide responsibilities, and jobs can also run in parallel, which is nice. Within a job, you have several sequential steps. A step is ultimately just executing a command, And if that command succeeds, so if it exits with code 0, then the step has succeeded. And if not, then the step fails and the job fails. So it's ultimately a shell command, but there are some nice abstractions on top of it, so you're not always literally running shell commands yourself. And then finally, a runner is the computer where a job runs. So we have exactly one job at a time on a runner. When you get started with GitHub, you typically use GitHub's provided runners, so you don't really have to think about it all that much. But you can also self-host your own runners, which I'll get into more later. So this slide is sort of the hello world of GitHub Actions. We have a YAML file called hello-world.yaml. On line 1, we're giving it a name. On lines 2 through 5, we're specifying the triggers for this workflow, so we want it to run when somebody opens a pull request. On line 6, we start specifying the jobs, and in this case, we only have one job, which is called hello world. We use this runs on key to indicate that we want it to run on a runner with the Ubuntu operating system. And then we get into our steps, which is a sequential list. And in this case, we just have one step where we run the command echo hello world. So when you run this type of workflow and open up a pull request, you'll see the workflow running. And it's basically just showing that, hey, I've started the workflow, and it's got a job that it's running. You can click for more details. So then you click into the workflow view, and it shows each of the jobs. In this case, we just have one. And we click into that job, and we can see that it executed our step, which just echoed hello world. So that's sort of where you get started with GitHub Actions. So when we started with GitHub Actions, we decided to do a proof of concept for some of our Scala projects that use the SBT build tool. So we started with a workflow like this for CI. We want to trigger it whenever somebody opens up a pull request to the main branch. And then we have a single job with a few steps. So the first 2 steps are checking out the source code and then installing Scala and the SBT build tool. Then we run SBT compile to compile the source code, SBT test to run our unit tests. We use Docker Compose to boot up some containers that we're going to use for integration testing. And then we run our integration tests, which in some cases we'll use those containers that are now running. And if each of these steps succeeds, then we get a green check mark on our PR, and we know that our code is working. Similarly for CD, we have a separate workflow. In this case, we use this workflow dispatch trigger, which basically means that we can go through the UI or through the API to start this workflow. We check out the source code, and we install Scala and SBT. This time, we're going to log into a Docker registry, because ultimately, we want to push up a Docker image. Then we assemble an application jar that contains our source code. We build a Docker image that contains that application jar, and then we push up that image to our Docker registry, at which point it's ready to be deployed into Kubernetes. So that was a good start, and it showed that GitHub Actions can work, but we're still missing a few details. So for example, we need to give SBT some appropriate memory settings. We need to configure SBT to bootstrap itself and its dependencies from an internal artifact repo. And then we need to do like at least 6 other things. And by the time we do all of this, we end up with a ton of YAML. And if we were to just take that YAML and copy paste it into all of our repositories, it would work for a little bit, but it would be a ton of duplication, and then inevitably it would drift, cause confusion, and just be really difficult to maintain. So we need some form of abstraction here. And one form is called the reusable workflow, which the idea here is that you essentially start with a regular workflow. You add some input parameters to it. Then you commit that to a repository. And then you can reuse it in all of your other repos. So we quickly reached for these reusable workflows. And the first one we started with is called reusable SBT CI. So like the name indicates, it's a reusable way to run CI on any project that's using SBT, as long as it adheres to some common structure. So you can see on the left here how we're using this reusable workflow on a pull request. And on the right, you can see that it runs as a job that's executing about 35 or 40 steps that set up the workflow, build our code, compile it, run tests, and so on. And I've zoomed in here on these steps. We particularly like splitting them up as granularly as possible so that we can tell, when something fails, we know exactly what failed. So to jump in a little bit deeper, on the left, we're actually using the reusable workflow, and the way we specify that is with this uses keyword. So we point at it, essentially, and it lives in another repository. And then we pass in some custom input parameters. So these are parameters that we've defined in the reusable workflow, and it essentially tells the workflow what to do. So for example, on line 9, we're saying that we want it to run S coverage checks to measure our test coverage. Then we say we want to use Scala style and Scala format to lint the code. And we tell it that we'd like to run integration tests and that we have a Docker Compose file that it should start before the integration tests run. And we say that it should also run assembly to make sure that we can still assemble our jar. And here we're saying that it should inherit the secrets that are available to this outermost workflow. So these secrets are used for things like authenticating to our Docker registry or to our artifact repository. And by saying that we can inherit them, we're essentially just giving the reusable workflow permission to access them. So overall, the reusable workflow implementation ends up being about 500 lines of YAML, which would be a lot to copy-paste. But using it in an individual repo is only about 10 lines of YAML, which is great because we use it in virtually all of our Scala repositories. So then we also have a reusable workflow for CD. This case, it's a little bit more interesting. I'll zoom in on these code segments in a minute, but the high level is that it's using actually 3 separate reusable workflows and running them sequentially. So the first reusable workflow is responsible for building and releasing our Docker image. As input, we tell it where the Docker file is and what the image name should be, and it knows how to do the rest, essentially build the code, build the image, and push it up to a registry. In the second reusable workflow, we're deploying the new image to one of our lower environments. So we use Argo CD to deploy, and the inputs here are the Argo CD app name, and then the image tag, which we've pulled in as an output from the previous reusable workflow. So basically pushed up the image tag, and then it tells us, hey, this is the new image tag. The third reusable workflow is essentially taking a list of values files, so Helm values files. Each of these specifies the latest image. It's taking that new image tag and overriding the previous image tag with the new image tag, and then making a pull request to our repository. So the pull request looks like this. You can see that we've got a series of Helm values files, typically one for each of our environments that we deploy to. We had the old image tag, and now we've replaced it with a new one. And an engineer will then take this pull request, approve it, merge it, and at that point our changes are staged and ready to be deployed, and we use Argo CD to synchronize them into our production clusters. So overall, the implementation is about 700 lines of YAML, but using it is only 30 lines, and again, that's great because we use this in a lot of places. So as a recap, reusable workflows are basically a way to share a workflow across many repos. We use them for standardizing CI, standardizing CD, for code scanning with different security tools, and for various kinds of linting, like for our Helm charts or our pull request titles. But in some cases, you don't actually want to reuse the entire workflow. You'd actually like to reuse a single step, and there's an answer for that too, which is called the composite action. So with a composite action, we start with an existing step, and we add some input parameters to it. We commit that to a repository, and then we can reuse that step in our other repositories. So if you've ever used action/checkout or action/setup Python or any of these other setup actions, these are composite actions. It's basically a bundle of code that somebody has packaged up and made available to you so you can run it as a step. So here's an example where we're using a composite action to send a message to our internal chat server. So on line 7 here, we're using this uses keyword, again, to basically reference this notify chat action. And then we're passing in some input parameters like the title, message, channel, and so on. The result is a nicely formatted message that lands in our chat server. And you can imagine that this is useful in a lot of different jobs. So it's very nice to have it packaged up as a composite action that you can use anywhere you need. So we've also used this composite action pattern for configuring our build tools so that they use an internal artifact repo, for running the Scala steward tool, and for caching and restoring build artifacts and dependencies in our jobs. So an interesting question here is, you've got all of these reusable workflows and composite actions. How do you actually verify that they're working, or who tests all of this YAML? So like I said before, we test all the code we write. So we also found ways to write automated tests for these workflows and composite actions. So on the left, we have an example where we're testing this reusable SBT CI workflow. We essentially just want to make sure that it's going to run end-to-end successfully on a simple project. So we've committed a simple SBT project into a repo, and then we're referencing this reusable SBT CI workflow to run on that project. And then the only input we provide is where it should find that SBT project. And if this runs end-to-end successfully, then you know that at least you can build this sample project. In reality, we have probably like 15 to 20 of these different test cases for different types of projects and different combinations of inputs. On the right, you can see we're testing the notify chat action that I talked about before. This case is a little bit more interesting because we're actually testing that when we give it a bogus input, it should fail. So it shouldn't silently succeed and then fail to send the message. So we check out the source code, which includes our composite action. We reference the composite action, and we pass it a bogus channel. Then we provide this continue on error flag, which basically says this job should continue running even if this individual step has failed, which is important. We give it an ID so we can reference its outcome. And in the final step, we're taking that outcome from the previous step, echoing it, and just grepping for the string failure. And if it contains the string failure, we know that the step has failed. So the only way to get through this workflow successfully is for that second step to fail, as we expect it to, and then for us to assert that it failed. You can think of this as CI for our CI and CD. We're not able to test all of the scenarios because some things are just stateful or difficult to set up for a test case. But we're able to test enough to where we can keep moving quickly on these reusable workflows and composite actions. All right, so now we've got these reusable workflows. They're tested, they're concise to use, and so we start integrating them into a bunch of our repositories. But we quickly hit a hurdle, which looks like this. So we've got an awesome testing job, except that it started 4 hours ago, and it's still waiting for a runner to pick up this job. So what's happening here is that we just have too many jobs and not enough runners to run all of them right now. So engineers are sitting around waiting in a build queue, which is not great. So one solution here might be to just add more static, long-lived runners that are just always on and sitting around ready for a job. The problem with this is that CI/CD workloads are very spiky, so they tend to quiet down on nights and weekends. But you can see otherwise, if we were to just try to pick a number of runners to keep around all the time, we would either keep engineers waiting in some cases, or we would have to have a ton of over-provisioned resources that are just wasting money and energy. So this kind of a workload is one where some type of autoscaling might be really nice to have. So fortunately, we already run a small Kubernetes cluster that we use to deploy development tools such as Argo CD. And it also just so happens that there's an open source project called the Actions Runner Controller, which is a Kubernetes controller that lets us deploy GitHub runners into Kubernetes. So at a high level, we can take this Actions Runner Controller, or ARC for short, we can deploy it to our Kubernetes cluster, and we get auto-scaling runners. So to dive a little bit more into how this works, we have GitHub and our Kubernetes cluster. We deploy 4 new resources into the cluster. We have a webhook server, this thing called a horizontal runner autoscaler. If you ever used a pod autoscaler, it's very similar. A controller, and then a runner deployment, which is similar to a regular deployment. When someone starts up a job in GitHub, GitHub actually sends a webhook event to our webhook server. At that point, the webhook server tells the horizontal runner autoscaler, hey, we need another runner to run this job. And then the controller takes that and adds a new runner to the runner deployment. So the new runner comes online. It's usually pretty quick, like on the order of 5 seconds maybe. It registers itself with GitHub, and at that point, job number 1 starts running on runner pod number 1. And I say pod number 1 because this is literally just a Kubernetes pod that happens to be running the runner software. We can do the same thing for a second job, and then for a third job, and so on. up to, of course, a limit of the max replicas that we've defined. And then at some point, these jobs complete, and our runner deployment scales back down to 0. So another important detail here is that we actually have multiple runner deployments, and each of them has its own autoscaler. This might seem weird, but the reason for this is that each runner deployment uses a fixed size runner in terms of the CPU and memory resources that are allocated. And you can imagine that resource requirements vary. So if you're just linting some YAML, that's very different than building a large Scala project. So each of these runner deployments has different sizes, and we can specify that a job should run on a specific one by using these runs on labels. So I've oversimplified it a bit, but you could think of it as we essentially have a small, medium, and large, and then when you write a job, you can say my job should run on the small one, the medium one, or the large one. So this is how things end up looking over the last month. So on the top, we have the number of nodes that we've used. On the bottom, we have the pods that we've used for our runners. And you can see there's a lot of variability here. And again, if we had just tried to pick a magic number for the number of runners that we want to have, then we'd either leave engineers waiting, sitting around in a build queue, or we'd be wasting resources by over-provisioning. So autoscaling is cool, but you can also take it too far. So every job when it starts is making a few API calls to GitHub. And if you start too many jobs at once, GitHub gets unhappy and ends up rate limiting you. And we found that this comes up very occasionally, but it has been an issue in some cases. We've gotten pretty good at balancing the right amount of autoscaling so that we don't get in trouble with GitHub. Another thing we can do that's useful within Arc is to have a custom runner image. So it's just a pod, and you can specify the image that you're running. So we built a Docker image that contains our most common tooling. So things like languages, build tools, and various CLIs. And the nice thing about this is that our jobs start up faster because we're not wasting time reinstalling the same tool over and over. And we also reduce the number of API calls we're making to GitHub. A final important topic here is observability. So we're running tens to hundreds of these pods at any point in time, and it's tied in very tightly to the engineering workflow. So we want to make sure that it's working. The various components of Arc, Actions Runner Controller, emit various Prometheus metrics, and these are pretty useful. In some cases, we also rely on structured logs to diagnose very specific issues. You can see that a log is tagged by the job ID, so it can be useful for figuring out what happened with a particular job. Overall, this works pretty well, but there are still some tricky cases. In particular, it's difficult to distinguish these sorts of nuisance failures. So when a job didn't run because autoscaling failed for some reason, or when a runner got killed because Kubernetes decided to get rid of the node that it was running on, or when a job failed due to rate limiting, a lot of that is still difficult to distinguish within just the metrics. But overall, we're very happy with Arc. We've been running it in production as our developer tooling gets for over a year now, and we'd recommend it, especially if you're already using Kubernetes. So the final section of the talk, I'd like to cover how we optimize GitHub workflows and jobs for Scala and SBT projects. The first thing that we can do with SBT is use this -client flag, which is going to start an SBT server in the background and minimize SBT startup times. So anybody that's ever used SBT knows that the startup times can be very long. So if you run a command like SBT version, which just prints the project's version, you're going to spend about 16 seconds in this case waiting for it to boot up, and then you'll spend about half a second for it to print the version. Less than half a second to print. But point is, long boot up times with SBT. So one thing you can do since SBT 1.4 is use this -client flag. And the first time you run it, you're going to also see the same startup time, but it's starting up a server in the background. And that means the second time you run the same command or any other SBT command on that project, it'll connect to that SBT server. And it's effectively a thin client that just connects, and you don't have to go through that whole setup process of loading up SBT. So you get a runtime of like half a second, which is really solid. The way we use this is we essentially just add this -client flag to each of our commands. And again, this makes it nice because we can split up the workflow into individual steps, so you can tell exactly what failed, and we're not paying this penalty of having a very long startup time with SBT. Here are some links if you're interested in digging into this. The second thing we can do is run a separate parallel job for every one of our sub-projects. This is particularly useful in SBT projects that have a ton of sub-projects. It can actually be faster to just run these all in parallel, and if you have the resources available, they will all run in parallel, which has been very helpful in some of our larger repos. It's not a silver bullet. You still have to watch out for rate limiting, but it is an option that you have. Finally, we found it useful to cache our dependencies and our compilation artifacts. This seems pretty obvious, but I'll go into the details of how we do it. So for dependencies in particular, we need to cache two directories. There's an SBT boot directory, which holds SBT's dependencies, and this Corsair home directory, which holds the project's dependencies. We also need to tell SBT about this, but you can just pass this in as a configuration parameter in your SBT ops file, or there are other ways to pass this in depending on how you run SBT. And then for compilation, we essentially just need to cache all of these target directories, which is where SBT puts the compiled artifacts. And when we do this, the next time we run a job that's been able to pull down the cache, it only needs to recompile the files that changed since the last time we pushed up the cache, which can also obviously save a ton of time. Typically, pull requests, if you're going quickly and making small changes or changing very small increments of the overall project. So I pulled some numbers here, actually ran this yesterday with and without caching on sort of a medium-sized project. And you can see that overall, without caching, it took about 213 seconds, and with caching, 40 seconds. So it's about a 5x speed up. And we happen to use a custom action for caching internally, but all of this also works with the publicly available cache action that's provided by GitHub. So there are some other fun topics that I did not have time to include. Maybe you can get your hands on the slides later and jump into these if you'd like. But at this point, I'd like to summarize. So what do we like about GitHub Actions? It's a pretty intuitive UX. You never have to leave GitHub, so if you like GitHub, that's great, and it's pretty easy to get started. There are some good constructs for reusability, these reusable workflows and composite actions, and you can even test them with a little bit of effort. Everything lives in source, which is particularly useful because there's no point-and-click configuration that can drift. And the documentation has been super helpful, and the community is strong. There's a lot of people using GitHub Actions, so pretty much if you have a question, it's probably already been answered. Some things we like about the Actions runner controller. So it's relatively simple to implement autoscaling, especially if you're already using Kubernetes. You can get your own runners without using Kubernetes. There are some other options, but if you're already on Kubernetes, yeah, it's pretty straightforward. The runners are ephemeral, which is super nice because you're not leaving around state for the next job to trip over. The documentation and community have also been solid here. And then obviously there's a little bit of room for improvement that we'd like to see or we'd like to help contribute to. One thing that would be nice is improving the observability for distinguishing these sorts of nuisance failures, like when a runner has died compared to sort of nominal failures like a test failing. Right now it's difficult to distinguish these in just the metrics. It would also be great to see some more flexibility in runner sizing. So right now you have to deploy a separate runner deployment for each size of runner that you want. It would be cool if the workflow could determine that dynamically. And it would be great if the runner software made more efficient usage of the API, especially during startup to minimize the impact of rate limiting. So with that, I'd like to say thank you to you all for joining today. If you're interested in learning more about the software and systems that we build, check out the 2 talks linked at the top here. If you want to know more about our products, check out tesla.com/energy or the energy and charging accounts on X. And then most importantly, if you're interested in helping us accelerate the transition to sustainable energy, check out tesla.com/careers or just come find me at the conference today or tomorrow. Thank you.